So students, in this lecture we will talk about magnetic field inside an ideal solenoid which is infinitely long using Ampere's Circuital's law, as you see on the sheet. Now for that, the first thing which I have done is I have drawn the pictorial representation of solenoid in the form of horizontal bars, as I explained it to you in the earlier chapter. Okay, now let's assume that we have to find the magnetic field somewhere here. So for that, let's draw a symmetrical rectangle, something like this, you know. Yeah, something like this. Okay, let's name it as A, B, C and D. Okay, and let's say the length of this is L, so this is also L. Okay, now the first thing is, remember, the assumption outside a solenoid is always that B is equal to 0. Now that is one. Number two, N is equal to number of turns per unit length where I is equal to in one turn, yeah, or I can say in one ring. Okay, now if I go back and check the Ampere Circuital's law equation, as you guys know, it is nothing but phi b dl is equal to mu naught I inside. Okay, and this is across the Ampere Circuital's law, Ampere Circuital's loop, which is ABCD. So this is nothing but Ampere's Circuital loop. Okay, very good. Now let's break this up into four portions. Now this, if I have to break this up, this can be it can be broken into phi b across AB, as you see this. Okay, and dot dl plus phi b dl bc plus CD integral dl, sorry, I missed b, correct, and finally integral b dl, which is dA. Okay, is equal to, now if you see here, let's go one by one. AB, in AB we have already assumed the magnetic field outside is 0, so this is 0. Okay, now if I talk about BC, in the BC this portion is 0, so this means from B till the point where it touches this bar is 0, and the rest of the portion, if you see, is actually perpendicular, this is perpendicular, this length is perpendicular to B, and remember the magnetic field here is in this direction inside the solenoid, as we have studied earlier. So the let me draw in this way. Magnetic field is in this direction. So if you see here, B magnetic field and length both are perpendicular. Hence, this is, if I have to write it in this way, B is perpendicular to L, and hence it is 0. Okay, coming on to CD. CD, we don't know, so let's leave it as it is, right? And if I talk about dA, so dA is again the same thing. This is 0 and this is perpendicular to, the magnetic field. So this is also 0. Finally, I can write it. I can write it that PdL is equal to mu naught I inside, or, and this is nothing but CD, correct? Further, if I talk about CD, so if you see in the CD, the length is actually, a magnetic field, this is this, and the length is this. So both are at an angle of 180 degree. So I can write it like this. This is B dot dl, by the way. So I can write it integral of B dl cos 180 is equal to mu naught I inside, right? Now to reiterate, here B, which is magnetic field, and the dl would always be in the direction of the flow of the current in the loop, which is this. We have assumed this, right? Hence the angle is 180 degree. So this can be written as cos 180 by the way is -1. So we can write it, we can take B is constant, so we can take it outside, is equal to mu naught I inside. Okay, let me write here. So now integral of dl, which is nothing here but CD. So this is nothing but dl plus dl, all adding all the small dls. The total length is L. So this becomes minus BL is equal to mu naught I inside. Correct? Very good. Or yeah, inside. Now if I have to find the magnetic field, remember this minus has no significance here. The reason being, if we have taken the direction of the current in the Ampere's loop opposite, then it would have been positive. So it just shows the direction. So it is mu I inside, or let me write it properly, mu naught I inside divided by L. So the formula, it's coming like mu naught I inside by L. But remember, we still don't know what is I inside. So we just know that in one we have n turns, right? We have n turns. So this length is L. So in L there would be what? N L turns. Correct? Now one turn has I current. So NL turns, would have NLI current. Let's substitute this here. So we will get B is equal to mu naught NLI by L. L and L cancels, so you are left with magnetic field is nothing but mu n I. Okay, so this is the formula for the magnetic field inside the ideal solenoid. Earlier we found it by the normal method, but this time we have found by Ampere's Circuital's law. So let me mark it. Okay, so with this I am taking a pause here. We will continue in the next lecture.